Hi guys, thanks for tuning in. In this video, I'm going to talk about how to deal with singularities. Now, probably the best place to start when we're talking about singularities is the Gauss-Green theorem yet again. So remember the Gauss-Green theorem says that if we have a closed curve C that encloses a region R, then as long as we don't have any singularities encapsulated by the curve C, we could either compute the path integral along the boundary or the double integral over the interior, and we'll get the same result either way. However, if we're in the unfortunate circumstance that we have one or more singularities in our vector field that are contained within our closed curve, then we're not allowed to use a double integral. The reason being is if we're accumulating over the interior, then we're going to end up hitting our one or more singularities as we integrate over the interior. So we're stuck with a path integral. The good news here is we're still able to do the problem. We just have to make sure that we use a traditional path integral when we're doing this problem. Now that doesn't make rotation and divergence useless though when we're dealing with singularities. It turns out there's a lot of interesting information we can glean about a vector field based on the value of divergence or rotation. So we're still going to keep those in mind. We just can't use a double integral to perform our calculations when we have a singularity encapsulated by our closed curve. So that's what we're going to talk about in this video. So for this first example, we're in a situation where we clearly have a singularity located at the origin, because our vector field is such that when x is equal to 0 and y is equal to 0, we're dividing by 0, so our vector field is undefined. So we've got a vector field that has a big fat singularity here at the origin. And then let's see what's going on with our curve. This is a fairly complicated looking parameterization that plots out looking like this teardrop shape here. All right, so the situation that we're in is we cannot use the Gauss-Green formula to perform our calculation as a double integral. A double integral over the interior of this region is out of the picture, not going to happen. On the other hand, the path integral along the boundary is also kind of undesirable because we have this weird shaped curve here. So let's see if there's anything else going on in this problem that can give us some information about how we could perform our calculation with a little bit less work than would be required to work with the given curve C. So we go ahead and we compute the rotation of our vector field, and it actually turns out to equal 0. And this is something that's actually worth verifying on your own. I highly recommend taking out a sheet of scratch paper, taking this vector field, and computing dn dx minus dm dy just to see how everything simplifies, and you are going to get that the rotation of the vector field is equal to 0. That means that we have like almost a gradient field, right? Our vector field behaves like a gradient field, a conservative gradient field, at every single point except for at the origin. So for example, if our curve had been translated a little bit, if we had a teardrop shape that was shifted just a little bit to the right where it did not encapsulate the singularity, I actually could use my double integral, and the double integral of 0 would equal 0, and the net flow of the vector field along my closed curve would equal 0. Unfortunately, that's not the situation that we're in. We have a singularity at the origin, our curve encapsulates that singularity, and there's nothing we can do about that. We have to do a path integral to compute this problem. The good news, though, is since the rotation of the vector field is equal to 0, the only swirl that can be added to this problem can come from the singularity. That is the only point that can contribute swirl in this particular scenario, because every other point is irrotational, right? Every point is irrotational except for at the origin. So what that means is as long as we have a curve that encapsulates the origin, we'll get the same result. Essentially, we can use a replacement curve. Instead of using this teardrop shape, what if we put the unit circle centered at the origin? We could do our path integral over the unit circle, and we're going to get the same result as the path integral using the teardrop shape. So here's my replacement curve. C2 is equal to cosine comma sine, where t goes from 0 to 2 pi. Now, by the way, remember, if we didn't have any singularities, then this would have been an entirely pointless process, because if the rotation of the vector field is equal to 0 and we don't encapsulate any singularities, then we would know the answer is 0. So that this little red box right here, that's what they're talking about. But we're in a scenario where we do have to do a path integral, but we at least get a little bit of a shortcut by using our replacement curve. All right, so let's compute this the old-fashioned way. Again, can't use a double integral, but I certainly can do the integral of field dot tangent for this unit circle here that I've placed centered at the origin. So I am using the curve cosine comma sine, and so you'll notice that every instance of x and y gets replaced with cosine and sine, and then I've got my tangent vector as well. Now, when you go ahead and take this dot product, you get a huge amount of simplification. This is worth verifying on your own, but you end up getting a Pythagorean identity in these denominators, and then when you take the dot product, you get another Pythagorean identity again, and your path integral works out to 2 pi. So we can conclude that the net flow of this vector field along our closed curve is counterclockwise. And when I say the curve right here, I'm referring back to my original teardrop shape, but it's actually true for any closed curve that encapsulates the origin. So it actually doesn't matter whether I'm working with this circle or whether I'm working with the original teardrop, or if I draw a star shape or some sort of jagged shape. As long as it encapsulates the origin, the net flow of the vector field along that curve is going to be counterclockwise with a value of 2 pi. By the way, you're going to notice with these singularity problems, very, very common to get 2 pi or some integer multiple of 2 pi. So if you get 2 pi or negative 3 pi or 6 pi or something, you probably did the problem right. I obviously can't guarantee it, but these are really common results to get some integer multiple of pi. All right, so what do you do if you've got multiple singularities? Well, do not despair. You're going to be just fine in a situation like this. For our vector field here, we could see that we do have singularities at 0, 0 and 0, 1. So now we've got 2 singularities to worry about. However, we still have a scenario where the rotation of our vector field is equal to 0. So we can kind of just repeat the same process, but just use small little replacement curves. So we have the same thing where the only swirl can come from singularities. We do have 2 encapsulated singularities, one at 0, 0, another at 0, 1. Let me plot those for you. So you've got 2 choices. Either one big circle that's big enough to encapsulate both singularities. Make sure not to make it too big, because if you do have a vector field with even more singularities, you want to make sure not to grab any extras, right? A really big replacement curve would be a bad idea in case you grab any new singularities that you didn't have before that are not supposed to be there. In this case, we don't really have to worry about that. We only have the 2 singularities. So that's one choice. Something else that you could do, especially if you have lots and lots of singularities, just 2 really small circles, each of which is centered at a singularity and each of which has a small enough radius to not accidentally grab the other singularity. So that's the technique that you want to use, especially if you're working in Mathematica. This is a great way to deal with numerous singularities without making any mistakes. And then we can sum up our results. So we compute the path integral for singularity 1, then the path integral for singularity number 2, and then we just add up the result from each of those 2 path integrals, and we're good to go. So here are the parameterizations for my 2 circles here. And the actual crunching of the numbers, I'm going to do this in Mathematica. Just like computing the rotation of my vector field. For this problem, I did that in Mathematica. Because if you look at the equation for this vector field, maybe you don't really want to be doing that by hand. Similarly, for our 2 path integrals, maybe you don't want to be doing that computation by hand. So here's the code that I ran through Mathematica. At the end of the day, it's like, you know, 6 lines of code, including a clear statement, to get this 12.5664. Now I got 12.5664 because I used n integrate. I think if you did this without the n in front of it, with any luck, you would get 4 pi, one of those integer multiples of pi, like we would expect. So here's my quick summary, guys. Um, if you have the rotation of your vector field equal to 0, here's how to deal with singularities. This is specific to the scenario where the rotation of the vector field is equal to 0. If you don't have any singularities, then the flow along your closed curve is going to equal 0. If you have a single singularity, just center a circle around that one singularity, do your path integral. And if you've got a bunch of singularities, then just center a bunch of tiny little circles, one around each singularity, and just make sure that your radius is small enough that you don't grab any extra singularities or double count any of your singularities by accident. And finally, the last thing I'm going to point out in this video is we have the exact same setup if we happen to have a scenario where the divergence of our vector field is equal to 0 everywhere except for at any singularities you might have. So if the divergence is equal to 0 and your curve does not contain any singularities, then the flow across is going to equal 0. If your curve does contain a singularity, just use a small replacement curve, probably a small circle centered at the singularity, and you'll get the same result by computing the flow across that small circle as you would have computing the flow across your original curve. And if your curve contains a bunch of singularities, no big deal. If you have a bunch of singularities, just center a small circle around each one, and then compute the path integral for each of those circles. Hopefully you've got Mathematica to do the work for you, and you sum up all of those results, and you are all set. All right, guys, thanks for tuning into this video, and in my next and final video for this chapter, I'm going to talk about differential operators.